my name is Erin Clark.
And I'm Morgan Harlan.
And I'm Ben Weaver, and this is Lab 4, Optimal Beam Collimation and Testing Radius of Curvature.
To begin the lab, we set up a beam expander as we did last week. We needed to design a beam expander that would use a 0.4 NA microscope objective and would expand the beam to be about 40 millimeters to fill the aperture of the shear plate. To accomplish this, we calculated that we would need a collimation lens with a focal length of about 450 millimeters with a pinhole with a diameter of about 50 microns. We attempted to align the 15 micron pinhole that was available, but the pinhole was too dirty and we ended up using a 25 micron pinhole instead.
So this is the setup we have thus far when we're checking the collimation behind our collimating lens. So if you look over here, we have our shear plate to see that we do have some parallel fringes, but you do see that they're kind of curvy, and that's indicative of there being some sort of aberration in the system. And it's likely that it's coming from either the microscope objective or from the collimating lens. But one cool thing that we notice is that these are very sensitive with air, and if you look very closely, the temperature difference off of my hands surrounding the beam is actually changing the OPD ever so slightly because of the refractive index of the space.
So we have now added a mirror to the system. This also creates another little source of error, which you can clearly see in the fringe pattern as we move it back and forth. You can see those little gaps right there. We can use the beam expander to set up with the shear plate to calculate the radius of curvature of a mirror. Using a low power mirror, we measure the fringe spacing, the shear distance, and the fringe angular deviation. We can then use these measurements to calculate the curvature of the mirror at two locations. We've measured negative 47 meters for the first position and then negative 58 meters for the position at the end of the optical rail. Averaging, we found that the radius of curvature for the lens was roughly negative 52 meters.
For the next part of the lab, we replaced the low-power mirror with a low-power lens. As you can see here, the fringes were not changed that much from the original. A small amount of tilt was introduced, which means the beam is no longer perfectly collimated and the light is slightly converging or diverging. Since this is a low-power lens, the light was not deviated by very much, which is why we can still see the fringes. We calculated the radius of curvature to be about 59 meters.
These measurements were taken using a protractor for the angular deviation of the fringes and a clear ruler to measure the fringe spacing and shear distance. Due to the sensitivity of the shear plate, we had to eyeball these measurements as a slight bump could cause the plate to vibrate.
So at this point of the lab, we're currently testing the focal length of our mirror using a 250 millimeter reference lens. So the first spot that we have our mirror, we're going to be observing fringes wherever the mirror is at the focal point of this lens right here. So essentially what's happening is the laser is coming to a point on the vertex of the lens, and then it is being reflected back, and so we see fringes there. However, there's going to be another spot that we observe fringes. So we're seeing fringes right now, and it won't be until we zoom out to a focal distance away from that point that we see fringes again, which should be coming up soon. All right, so right about there.
As you can see here, the high-powered mirror introduced a lot of aberrations into the system, which is apparent in the fringes on the shear plate. The shear plate shows us the derivative of the actual aberrations in the system due to the combination of the two beams, which are offset by some shear distance. Since we see the third-order aberration of coma, we know that that spherical aberration is in the system.
So essentially right here, the beam path is kind of like perpendicular to the curvature of the lens. So each part of the laser that's like hitting as it's like diverging out is going back to that focus that we initially saw and is propagating back through. And then because it's focused here and going back through, we see collimation here again.